Welcome, everybody. My name is Kees Noek, and it's my great pleasure to finally deliver this keynote for MMM 2021. I would like to talk about real-world video AI. But before doing so, let us first look at some highlights of what the field has achieved. So this is action classifications for short trimmed clips, and look how well the classifier is able to predict all kinds of actions, ranging from popular sports to maybe more uncommon activities. It can classify them all really, really well. Here's another example of the slow-fast network by Feigenhofer et al. That is able to not only classify the activity, but also localize when and where they happen. So this network comes with a slow pathway operating at low frame rates to capture spatial semantics, and it also has a fast pathway operating at high frame rate to capture really the motion at fine temporal resolution. But there is more. This is an example of tracking, where the goal is to track an object given a bounding box around the target to track in the initial frame. So here I show a visualization of three trackers. They are already a bit old, but they illustrate the progress very well. So the goal is to track Yoda. And what you can see here is that all three trackers, indicated by three colored boxes, are able to track the object well, especially if he does not move too much, but also when there is a camera viewpoint change, most of the trackers are still able to localize the object of interest. Here, the target has disappeared, and some trackers reside to just providing the center box in the frame. But some trackers, like the sync tracker, is able to do a really, really good job. So here the object is again gone. Here it comes back, and the tracker is able, as you will see in a bit, to redetect the object of interest. So this is real progress, look. And despite all the in-plane rotations and deformations, even this sync tracker can do a really, really good job. Here the object disappears again. Some trackers have difficulty finding the target. Sync makes some mistakes. But once Yoda returns, Sync will do a good job. So here again the mistake. The target is back, and the tracker is able to redetect. Now, isn't that great? Here's another example from my lab, where the goal is to identify the actor and the action that are provided in a textual description by identifying all their pixels. So here the goal is to find the woman in the purple dress who is running. And then the algorithm is able to identify those pixels in the video that correspond to this textual description. Now, of course, the segmentation is not perfect. There's still quite some mistakes, but the result is actually quite reasonable. And if you would have told me that this would be feasible in such a short time span, I would be really amazed. And what is nice about this algorithm is that if you change the query, so now we are looking for a gray dog that is running on a leash during a dog show, the network is able to switch to the new actor and the new activity. And while this may seem easy, notice that there are many other dogs in the background visible, and the algorithm is still able to identify that dog that corresponds to the text query. Here's another example from CFPR last year, where we looked into group activities. So we're not only interested in identifying the individual activities of the actors in this volleyball game, but also in identifying the group activity, which in this case is left set. So really the field of video AI has made tremendous progress in the last decade. And this is, of course, also mostly due to deep learning, large data sets and clever optimization. So this is where we are. We can do a really good job and classify basically anything we want, as long as we have large amounts of data, large amounts of labels, and that the visual diversity in the domain is not too big. Then you can really get good results for any problem you want to solve. When we are moving to a more open world recognition challenge, where it is not completely clear what we will see at test time, the challenge becomes more difficult, and that is where we as a community are moving, right? So slowly we are getting into how can we expand our recognition abilities to recognition in an open world that we have not seen during training. And now there is a problem, which I refer to as the video understanding paradox. So as understanding becomes more and more specific, it is really unrealistic to assume that ample examples to learn from will be commonly available. So here is a real problem from Amsterdam, where people can steal your bike. Now, how do you go about recognizing a bike thief? Of course, one could label hundreds of examples, but the problem is that bike thieves don't want to be caught, right? So they prefer not to be caught also on camera. So it will not be easy to find hundreds of examples of a bike thief in all kinds of videos that you like. Not to mention providing box annotations around the object of interest, or even pixel annotations to further improve your algorithm. Of course, we are also interested in causal relationships, because walking with the crowbar by itself may not be harmful, but once you start to use it for a locked bike, all of a sudden it becomes a theft. And understanding this chain of relations will require annotations as well. So that brings us to the following problem. So if we want to continue labeling data, train your network, report results, and continue forever, we will reach a dead end for open world recognition, simply because the amount of data and the amount of labels will not scale to the amount of data in the world. So the mission of my lab is to understand video in an open world and to use as little dependence on supervision as feasible. And that is also what many have identified as a good challenge to work on. Now, this is hard, but luckily there are all kinds of tools from machine learning that can help. So let me first provide you with a brief review of modern machine learning tools. So first, there is self-supervised learning. So rather than labeling data and learning your deep learning network based on the provided labels, you can also use the structure that is available in video and image data as sort of pseudo labels. So here is a paper from iClear 2018, where there was a self-supervised approach using a pretext task of rotating images. So by rotating an image 90 degrees, 180 degrees, and so on, you sort of create artificial labels, namely the number of degrees becomes the label. And then you can learn your network to predict this rotation. And this is a very good pre-training task, because the network weights will be initialized already in a very effective way. So if you want to then leverage this network, you only need a few labeled examples for fine-tuning to get really good results. And people are making lots of progress in self-supervised learning. But again, you still need labels to fine-tune. And also domain generalization to an open world has not really been shown for self-supervised learning. Then there is meta-learning or learning to learn, where people typically use two optimizations. The first one is a learner, which learns a new task, like a few-shot classification of dogs or pianos based on a few examples. And then there is the meta-learner that trains the learner, so to say. So even when you encounter a class at test time that you have not seen before, the meta-learner sort of knows how to attack this problem. Then there is domain generalization, and here the task is to, given domains that one has seen during training, for example, photos, art paintings, and cartoons, the task is, can you build an algorithm that generalizes to unseen domains? So, for example, the sketch domain. And here the challenge is that no sketch images have been seen during training. And how do people typically go about? Well, they learn a domain invariant representation. That's one popular approach. And another popular approach is to generate artificial domains using generative models during training, so sort of like to anticipate what you may see at this time. Naturally, those ideas can be combined. So meta-learning and domain generalization in a single approach. And this is work from my lab on few-shot domain generalization, where we looked into the problem of, or the process of batch normalization, as this plays a crucial role when training deep neural networks. But the problem with batch statistics is that they become unstable with small batch sizes, like we have in few-shot learning. And they were also unreliable when the distribution shifts change. So we proposed the meta-norm algorithm, which tackles these issues by leveraging the meta-learning setting, and it learns to infer adaptive statistics for batch normalization, even across domains. And then there is zero-shot learning you may be familiar with, and here the goal is to train images based on some attribute representation that are easy to obtain, for example, from knowledge sources like Wikipedia. And then when you encounter a new class, one can detect the attributes in these images and try to infer what this class is given the attribute evidence that is detected. Of course, the attribute classifier still needs to be trained and labeled. So essentially you move the image classification labels to attribute labels, but the hypothesis is that less of those will be necessary. So these are some modern machine learning tools that are used for, that can be used for real world video AI. Today, I would like to talk about a different topic, and that is the value of similarity when doing real-world video AI. And the talk is separated into three parts. I would first like to discuss with you sensory similarity, then spatiotemporal similarity, and finally, semantic similarity. So let's first discuss sensory similarity, and this is based on the CFPR 2021 paper together with Yunhua Zhang and Ling Xiao from the Inception Institute of AI. So here we are looking at repetitive motion, and repetitive motion is everywhere, in sports, in music, in urban environments, and also natural environments. So if you look at it, you will see repetition everywhere. And the topic of repetition estimation in video is a classical problem in vision that many have attacked in the past years. And often it is assumed that these repetitions happen in a stationary world. So when repetitions happen in the stationary world, you can represent the video as a one-dimensional fixed period Fourier signal that preserves repetitive motion structure. Unfortunately, the assumption of static and stationary videos is inapt for the open world scenario where we ultimately want to recognize repetitions. So in this example below, this shows a rower who is accelerating at a certain point, as plotted in the time-frequency space. The vertical axis of the spectrum denotes the wavelet scale, which is inversely proportional to the frequency. The sudden acceleration appears as a shift of the maximum power in the time-frequency space. The Fourier transform, commonly used in the literature, is unable to handle such a non-stationary video. So we have worked on repetition estimation in a non-stationary world. And rather than relying on Fourier, we consider the wavelet transform of optical flow features. So what we did here is that we first segment the foreground motion with the top row, the blue segments, followed by optical flow computation, the yellow arrows, and then we extract 6 zeroth and first order flow signals. And finally, we decompose them into a time frequency spectrum using the continuous wavelet transform. And by doing so, we can also recognize repetitions in non-stationary worlds, at least better than the ones based on Fourier domain. Then there is the dataset world, and these are 2 papers from CFPR 2020 that look at repetition estimation in video by proposing 2 new datasets. So the one I'm showing here is the Countix dataset by Dubedi et al. And they have captured all kinds of repetitions as they happen in video, and also add the counts to these videos, as this is the means to evaluate how often a repetition occurs in a video. And by introducing these datasets, they opened the problem for deep learning. And all of a sudden, we can train a deep learning network based on the data that is provided. So both approaches introduce deep learning into repetition estimation. But then there are also challenges when you rely on deep learning. So there are, for example, open world challenges that are unseen during training. And I will show you a few examples. So this is a low quality video. So all of a sudden, your nicely recorded video seen during training do not generalize well to this example. Or all of a sudden, the light is gone, and this activity happens in the dark. This is also a very nice one. Somebody is playing tennis, but then the actor of interest is disappearing out of sight. Here's another one, camera viewpoint change. So very hard for video algorithms. Very complex sceneries, so it's very hard to see where to look and what is the activity that's going on. And here is another example showing a scale change. So the scale of the swimmer changes as he progresses towards the camera. This is very fast motion, also very challenging. So how can you count the repetitions in this one? So we thought about this problem, and what we came up with is a new perspective on video repetition estimation. And of course, this perspective is multimodal. Multimedia is the way to attack this problem. And how do we do so? By not only considering the sight, but also leveraging the sound signals in the videos. So we contribute the first audio-visual models with a sight and a sound stream for repetition estimation. And because this is a new problem that nobody considered before, there was no ideal data set to study this problem. So we contribute also 2 sight and sound datasets for video repetition estimation that we repurpose and reorganize based on existing datasets. Now, the basic model is simple. So we have a side stream, which is essentially an S3D network that predicts the counting result per input clip and repetition class. And the repetition class is a latent variable, a hyperparameter that we optimize during training. The sound stream is a ResNet 18, predicting the counting result per sound spectrogram. And again, using this repetition class hyperparameter. So nothing special so far. Then we have a temporal stride module, which is more dedicated to the problem, and it selects the best stride per video for the side stream based on visual and audio features. So the periodicity of a repetition may vary, and to make sure that we capture it in the right temporal stride, this module does that job. And it is not only based on visual information, but can also leverage the audio signal. So this is where the multimodal fusion happens, so to say. And then we also have a reliability module, which essentially decides what prediction to use. So sometimes it is wise to rely on the visual, on the side stream only. In other occasions, it is better to rely on the sound because it provides a better signal. These are the basics of the algorithm. A more detailed view of the model is slightly more involved. I'm not going to go over all the details and network settings that we use, but you can find them all in the paper, and the code is also available. Then we introduced two new datasets that are based on the Countix dataset that was provided by DeepMind in CFPR 2020. The Countix dataset contains some videos with audio, but not all videos have audio. So we selected those videos and classes that come with audio, and we created what we call Countix audio visual. So for a total of 1,800 videos that cover repetitive activity categories, and they all have a clear sound or background music. And we created a training, validation, and a test set. In addition to that, we also created Extreme Countix AV, and this is a test set only. It contains 156 challenging videos from Countix AV that we supplement with another 58 videos from VDG sound. So this is also a video dataset emphasizing sound activities. And this is interesting because in this dataset, the site conditions are too poor for counting, based on visual information only. And the splits and partitions of these datasets are also available. So here are some examples of clips in this Countix AV and Extreme Countix AV dataset. I will show a few more in a bit. Let us first look at an ablation of the model. So here we analyzed the benefit of the various model components, and the metric we use is mean absolute error. So we measure the error in the counting results, so how many repetitions happened in a video, and the lower the error, the better. So if we rely only on the side stream, we obtain a mean absolute error of 0.33. When we only rely on the sound stream, the results are worse. This is not completely surprising, but still actually quite good. And here the results are 0.37. When we introduce the temporal stride module based on site information, we obtain a mean absolute error of 0.31. So the error is reduced quite a bit. And if we use fusion based on a simple averaging of sight and sound, we get 0.30. So again, an improvement. But if we use our full sight and sound model, including this reliability module that predicts what module to trust more, so to say, we obtain our best result with a 0.29 mean absolute error. So the bottom line here is that all modules matter, and reliability estimation is preferred over simple averaging of the individual modalities. So this is the comparison with others. So we could compare with other work using the site data sets that are available in the literature. So these are provided on the left. And on the right, we also report results where feasible based on the sight and sound data sets that we introduce. Now, what is of interest here is that if we use our sight model, our sight only model only, we already get quite good results on the existing sight data sets as well as our sight and sound data sets. When we add sound, results tend to, when we rely on sound only, results tend to be a bit worse, especially on the data set that emphasize vision. When we look at the data sets that emphasize sight and sound, it varies. So on Countix AV, results are slightly worse, but on extreme Countix AV, which you could argue is more oriented towards sound analysis, results improve. And in any case, when we combine sight and sound, results are always better. So sight-only model already good, adding sound further reduces the counting error. This table I find more interesting, and this shows results on the extreme Countix AV test set, where we have identified a number of open world challenges and report the influence of sight, sound, and their combination. So here you see the open world challenges like camera viewpoint changes, cluttered background, low illumination, fast motion, disappearing activity, scale variation, and low resolution. And what we notice is that, well, sight provides the baseline with an overall mean absolute error of 0.39. And when we rely on sound, results are much better on this data set, because these open world vision challenges all of a sudden have limited impact on the sound signal. And when we combine sight and sound, the results are always better than sight only. So let me show you the same video I showed before, but now with the audio. And what we see here is the video together with the predictions based on sight, sound, their combination, and the ground truth. So the quality of the video is bad, but the quality of the audio signal is quite okay. In here, low illumination, but the sound is good. Clear? The actor disappears, but the sound continues. Sound is invariant to camera viewpoint. And also the complex background, has no impact on the sound. Same for scale change. And the fast motion is also addressed well with the sight and the sound. So sound can play a vital role, especially under harsh vision conditions. That is essentially the takeaway of this experiment. So the sensory similarity between sight and sound helps generalization to an open world. Next, we're going to look into spatiotemporal similarity. And this is again a CFPR 2021 paper together with Peng-Wan Yang and Pascal Mettes, both from my team at the University of Amsterdam. So we consider the problem of few-shot classification. And the canonical paradigm is to pre-train a network and then provide a few labeled examples to classify the unknown object in a query image. This can be easily extended to few-shot detection, so not only classify what object is in the query image, but also localize its bounding box or its pixel segmentation. So then what is needed is support images are not only provided with the class label, but also with the bounding box around the label. Then one can train a network that will predict the class label and also the box around the object in the query image. Together with Tao Hu from my and co-authors from my team, we proposed few-shot common object localization in space. So here the goal is to localize the common object in the query image without any label and box annotation. So what is different here from the traditional setting is that in the support images, we don't provide any label. We also don't provide any box information, but our network is still able to classify in a query image whether it contains the object and where it is localized. So rather than using labels, here we are using spatial similarity, right? So the idea is that there is a common object in the support images. We just don't know its class label, but it's also not important to identify the same object in a query image. So how do we go about in this work? So we have a backbone network, your favorite network, let's say ResNet 18. Then we have a module that computes spatial similarity among support images and query image. A feature reweighting module that highlights that some support images may be more informative and valuable for the final detection result. So to give them a higher weight. And finally, a detection module that puts the bounding box around the most salient object, so to say. So this can localize the common object in the query image without any box annotation. At ECV last year, we extended this work to action localization in time. So given an untrimmed query video, can we find the common action somewhere in this video based on a few provided trimmed support videos that contain the same action without knowing its action class label. This network contains a mutual enhancement module to simultaneously complement the representation of the few trimmed support videos and the untrimmed query video. An alignment module that iteratively fuses the support videos into the query branch, and a pairwise matching module to weigh the importance, again, of different support videos. Now, today I would like to talk about few-shot common action recognition in time and space. So given a few trimmed support videos, without knowing their label, but we know that they share the same common action, we introduce a few-shot transformer that is able to identify in an untrimmed query video the same activity as indicated by its bounding chuplet around the activity. What is interesting about this approach is that it does not need any action class label or any temporal or any spatial annotations. This is all inferred from the data. So here's an example. Here we have 5 support videos, and this is what we aim to achieve in the query video. So the blue box is the one-shot prediction, where we have only one support video, and the red box is the 5-shot prediction, where we provide 5 query videos. So our goal is to identify the common action with this bounding chuplet. Now, for our approach, we are inspired by object detection, like so many approaches in activity recognition. And in particular, we look at the object detection transformer DETR by Carrion et al. That was proposed at ECV 2020. So transformers for object detection have some nice properties. because it avoids this needle in the haystack problem that proposal-based methods typically have. So they reduce an input image to a huge amount of proposals, and then in the second stage, the network should be able to identify the right proposal that corresponds to the objects of interest. So rather than using proposals, the data is completely end-to-end, and it provides powerful relation modeling capability inside the encoder-decoder structure of the transformer. Now, we use a similar idea for our common action detection in space and time. So the overview of our method looks like this. So we have a trimmed support videos as input, together with an untrimmed query video. We first run them through our favorite video backbone, let's say i3D. This computes features. And then we have our common attention block. And this is a new addition that we introduce into the network. So this common attention block is built on the self-attention mechanism and also the non-local structure. And it extends the self-attention mechanism in the transformer to self and cross attention. So here we have the few shot transformer. So the features go into the encoder. We concatenate them. The one for the support videos and for the query videos goes into the decoder, and then eventually we will do our prediction using Hungarian matching between the boxes. It predicts a foreground box and a background box, and we link them together using dynamic programming. And that will be able to provide the tuplet into the query video. Now, common action localization in space and time did not exist, so there was also no dataset that we could use for this purpose. So we redefined two existing datasets. So we took AVA and UCF, and we repurposed them for our goal of common action detection. So here you see the statistics of the two datasets that we created. So AVA is a larger data set. UCF is a bit smaller, but tends to have longer durations and also less actions. And again, these partitions are publicly available. So here we do some ablations on common AVA. And on the left, the influence of having a encoder and decoder in the transformer architecture for both support and query features. And one can see that all the components matter. So although we can do a good job based on a decoder only, combining it with an encoder with both support and query features further improves the results. And the number we report here is the frame level mean average precision, with an IOU threshold of 0.5 for both datasets. I didn't discuss, but positional encoding is also an important element in the transformer architecture. So this is typically part of the encoder that you can do, again, for both the support and query features. And what we notice that also here, this positional encoding is best included in both support and the query, because this leads to the best results for both the one-shot setting, where we have only one example in the few-shot setting, or the 5-shot setting. Then we also looked into the influence of the length and the number of support videos. So let me explain this plot. On this axis is the frame MAP value. So the higher, the better. So the higher, the better the score. Here we vary the length of the support videos from only 5 frames per support video up till 25 frames per support video. So what this shows is that the longer the support videos, the better the common action detection result will be. And then we also vary here on this axis the number of examples in the support video. So ranging from 1 example to 5 examples. And again, the more examples that are provided, the better the results. So the more content it sees in the support videos, the better we will be able to identify the common action in space and time. Now, that might be an obvious conclusion. So we also looked into what is the influence of noise. So let's say we have, and this is evaluated for the 5-shot setting. So when we have no noise, so all the 5 support videos contain indeed a common activity, then we can get a frame level MAP of 28.1 on Common AVA. Now, what if we introduce some video level noise? So we replace one support video with another video that comes with another class. So the common action assumption is broken in this case. Accuracy drops, so it drops from 28.1 to 26.8, but it is not so bad actually. We also replaced it with another video that contains no activity, and we see the same results. A little bit more drop, but not seriously so. When we increase the number of support videos further, so now 2 out of 5 support videos contain either a video of a different class or with the same class, the results drops further, but again, it's still relatively stable. We also injected noisy frames in the videos to further test generalizability. And what we can see here is that when we increase the number of noisy frames from 2 to 8, results start to deteriorate. But again, it is still quite robust. It does not collapse. Now, next we evaluate common action in time and space. So the task did not exist, so there were also no baselines. So we constructed 2 baselines based on existing action detection approaches using either a 1-stage end-to-end approach or a 2-stage baseline using proposals and then selecting the right proposal. And our few-shot transformer obtains favorable results on both the 1 and the 5-shot setting across both datasets. So for as well common AVA as common UCF. And what is more, we do not need any proposals or other predefined components. So this is completely end-to-end. So here you see some results. So on top, the support videos, on the bottom, the query videos, and blue indicates the results for 1-shot example, so when we have only 1 example in the support videos, and the red one is the one for the 5-shot examples. So you can see that here a mistake is made for the 1-shot setting, but it is covered for the 5-shot setting. So the 1-shot setting also captures the person who is walking, but we are looking here for a person on a bike, and that is corrected for the 5-shot setting. Then we also considered a scenario where we identify the common actions in the temporal dimension only. So we forget about the spatial dimension and only look at the temporal dimension. And then there are 2 related words. So our own work from ECV 20, and there was also a 1-shot alternative that could do 1-shot temporal localization by Feng et al. And when we use the same backbone as theirs, this C3D backbone, we outperform them by a good margin, although we are not even designed for this setting. And when we replace the C3D backbone with the better I3D backbone, results improve further. Now, we also extended our approach to common action recognition per pixel. And this is actually quite straightforward because we simply add a mask head on top of the decoder outputs from the transformer. And this predicts a binary mask for each pixel inside the predicted boxes. And here we see some qualitative results. So the support videos all contain a running dog. And in the query video, we identify the dog. And what is interesting here is that we have two instances of dogs, and they are both accurately segmented. So this is a nice result because we do not need any class labels. We do not need any bounding boxes. We do not need any temporal bounds. And in this case, we don't need any pixel annotations. So with this approach, we can expand beyond a vocabulary of labels that we have during training time. And all we need is a few examples with a minimum of one to expand to unknown territory, so to say. So that concludes the second part of this talk. And next I will switch to semantic similarity. So far, we have considered a supervised scenario where either labels were available or few labels were available. Next, we are looking into the scenario where we don't have any labels nor any videos available at training time. And for this purpose, we rely on semantic similarity. And this is based on a paper that appeared in IGCV this year, together with Pascal Mettes and William Tong from my lab at the University of Amsterdam. So the common tactic for zero-shot learning is to rely on attributes. So given an image of a zebra or a panda, we are able to distinguish between the two based on the attributes that are defined, like is black, white, has a tail or no tail, lives on the land, is small or big or medium, etc. This is the common tactic. A downside of zero-shot learning is that attributes need to be defined a priori and they need training data as well. So we prefer another approach to zero-shot learning. And our inspiration comes from language, where we observe that most object categories are common across cultures, and this leads to a similar formation process across languages, in the sense that children first learn object nouns, and then they learn action verbs. So the hypothesis here is that given a large vocabulary of object nouns, it becomes easier to learn action verbs. And the nice thing is that the vision community has put a really large effort on making object labels and classifiers for images commonly available. And we can build on this common knowledge on images to generalize for video, so to say. Already in 2015, together with Mihir Jain and co-authors, in my lab, we worked on an approach that's called objects to action. And what we did here is that we used a word embedding that is spawned by a model of 15,000 object categories that we learned from ImageNet. So based on ImageNet images and labels, we trained a deep net, I believe it was an AlexNet in the days, that could predict presence of one of 15,000 object categories. So we represent a video based on this vector of classification scores. And then at test time, we simply look for what affinities could we find in object action space. So here spanned by a word2vec model to find those actions with, or those objects with the high scores to determine the most likely action. So to give you an example, if the horse classifier fires in this unseen video, that tells you that the likely actions here are, for example, horse riding. So we find these affinities using a Google News corpus and a Word2Vec embedding. And we train our video representation is based on ImageNet, images and labels only. So it has not seen a single video during training. It just relies on a pre-trained AlexNet, predicts the scores, and finds the affinity in text embeddings. We compare this with a traditional attribute-based approach. So here, the action attributes need to be trained in advance. So we split the UCF training set in two partitions, even videos and odd videos, and we use each split to train our action attribute classifiers and then report results on the other partition. So, and action attributes here can be things like torso twist and look down. Notice that these require annotations as well. So when we train a representation based for zero-shot learning, we get an average accuracy on UCF 101 of about 15%. And instead, if we use our object representation based on the 15,000 ImageNet object classes, we obtain an accuracy of 38%, so a considerable increase. And what is the nice part here is that no videos are needed during training. So where the attributes need to be trained on video material, we could train the object classifiers on image data only. So we transfer from the image domain into a semantic domain that transfers well to video as well. Now, then you can do all kinds of funny things. Like this is the TUMOS video dataset. And we try to retrieve never seen actions. So we came up with imaginary actions and we look at the top 5 retrieved results. So for example, in the first column, we look for a fight in ring, which is not an activity that is defined in TUMOS, but it nonetheless generates some relevant results. And also the dancing is not an activity in TUMOS, but we could still get good results. For the hit wicket, it seemed to me like reasonable because at least we see some cricket going on, but I've been told by the experts that none of them contain a hit wicket, so there's still some room for improvement here. We also generalized this approach to action localization. And there we used action proposals, so action 2 proposals. So these are possible locations of an action in space and time. And typically hundreds of those proposals are generated for a video. So then what we did, we encoded each of those hundreds of tuplets with our 15,000 object representation. And then we can do zero-shot prediction for each of the tubes individually and simply select the best one and return that as the action localization result. Here we have some qualitative results showing the action localization. So in yellow, the ground truth, and in green, our object to action prediction. So you can see that for this diving activity, it works quite well. Also for the skateboarding, our predicted tublet follows the ground truth closely. And we also have a failure case here playing golf. So the ground truth also includes the golf player, where our selected tublet emphasizes on the golf club instead of the actor. So I think the takeaway here is that objects to action is able to localize actions without any ever having seen any video examples during training. So I think that is the remarkable part. We further improved upon this work at ICV 2017 together with Pascal Mettes, where we added more spatial object awareness into the embedding for zero-shot action classification and localization. And we did so by defining what we call object priors. So our first object prior is the location of the actor. The second one is to use location of objects, and the third one is to use spatial relationships between actors and other objects. And again, we build on what is made available in the vision community. And this time, actors and objects based on faster RCNN for bounding boxes and scores, which are then pre-trained on ImageNet and MS Coco. So for actors, we use the person class as defined in MS Coco, and for objects, we use the 79 remaining objects from MS Coco. And again, we rely on Word2Vec to select those objects that have the largest similarity inside the Word2Vec embedding. So the idea of the actor localization prior is the following. So the higher the likelihood of an actor in a box, the higher the overall action score. So we use the prediction for each box that is detected in an image frame. And if it is a person box, we use this score. And the higher this score, the higher the likelihood that an action is happening in that frame. The second prior is the location of an object. So where in objects to action, we use the object class score. Here we also use the object bounding box. And relevance of objects given a certain action, let's say kicking a ball. So we can expect that besides having an actor visible, there should also be a ball visible. This affinity is again learned from Word2Vec embeddings. So ideally then, this ball detector is one of the 80 objects that you have available in your vocabulary. Now, the third prior is spatial relationship between actors and objects. And this shows the intuition. So here we have two actors being visible. And we also have, we are looking for the activity skateboarding. Now, the relative positions of objects and actors, you don't need videos to mine these relationships. You can again rely on images, static image data only. For example, the images that are provided in MS Coco. And from these datasets, you can learn priors that it's more likely for a skateboard to be below a person rather than be next to a person. So if you have to decide between those two boxes, which one is the most likely location of the action skateboarding, then you should go for this one, as the skateboard is below the person and not next to the person. So here are some more qualitative results for spatial relationships. So if you're looking for, and these are all relative to a human actor. So a backpack tends to be on the back of a person. An umbrella tends to be above a person. A stop sign tends to be above. And when you are photographed together with a sheep, a horse, or a giraffe, they tend to be on the sides of the image composition. Now, we need to combine all these priors. So this has a highly involved score function, but notice that we do not use any training data, right? So these are all combined based without any training. So we use the likelihood of individual actor boxes as identified here. Then the relevant objects, also again with the score, together with spatial relationships prior, and these are combined together to find the action horse riding over here. This is on an individual frame to make it suitable for temporal dimension. In video, the individual boxes are linked through dynamic programming, a standard procedure from the literature. Now, what is the effect of being spatially aware? So we did an experiment on UCF sports for both action classification, so what action, and action localization, where we mean with localization both space and time. So if we only have an actor detector, that is actually by itself a reasonable prior. So for action classification on UCF sports, that gives us an accuracy of 8.5, which is, well, is better, much better than random. And also for localization, it gives a reasonable result. But as soon as we start to add objects into the equation, so knowing that objects are related to certain actions and detecting their presence, it really helps. So if we detect only one object, the score already doubles, more than doubles for both classification and localization. And finding the ideal number of objects is dataset dependent, but in both for UCS sports, we found that detecting 5 objects in general leads to good results. So the bottom and adding the spatial relationships on top further improves the results. So the bottom line is that object locations and spatial relations really help to discriminate unseen actions. Now, we extended this work to also include semantic priors, so in addition to the spatial priors. So where the spatial priors enable spatiotemporal unseen action localization, they ignore the context from surrounding object classes. So we expand the object vocabulary of 80 COCO classes and detectors, so to say, to 13,000 image level classifiers, again trained from ImageNet. And those are based on a Google Net pre-trained on the ImageNet categories with a rate of 2 frames per second during testing. And we introduced 3 additional priors to really capture the semantics of the objects. And those semantic object priors are summarized as follows. So the first one, emphasis on semantic disambiguation. So, and for this we use multilingual embedding. So rather than relying only on an English language embedding, we use the fact that objects and actions go together in many languages, and we can reduce ambiguity by relying on multiple languages. So here in the example, the object football is enforced because its semantic similarity is high across languages for both English and Dutch in this example. In B, we consider object discrimination. So often many objects are visible, but which one is the most distinguishing one to get to the action of interest? So here, for example, we have the action kicking and walking. And we find objects like goalpost and grass. Now, the importance of grass is decreased or should be decreased, as it is also relevant for other actions, while the opposite happens for goalpost. So here really having the goalpost detected is a really important cue for the actions of interest to occur. And one can use knowledge hierarchies like WordNet and dedicated score functions. In C, we have another property of semantic priors, namely object naming and preference for basic level entries. So in this example, the importance of football is increased again, and the importance of adjudicator is decreased, as football follows the basic level object naming in contrast to adjudicator, which, by the way, is another word for referee. So in all cases, the closer to the center of the action embedding, in red and orange, the higher the object relevance. So this is the basic idea between the semantic object priors. So let us first look into the benefit of being multilingual in the word embedding. So here we show pairwise multilingual's evaluation of 6 languages that we took from FastText, which is pre-trained on 157 languages by Grave et al. And what you see here, that for each row, we visualize the impact of adding another language. So English is already very good by itself. So adding more languages does not really benefit the result that much. Only by adding Dutch, results improve. So English and Dutch is a good combination, so to say. When we look at Dutch, which is by itself much worse than English, but adding multiple other lingual embeddings then really pays off. And the same observation we observe for the other languages like Portuguese, Afrikaans, French, and German. So being multilingual in your embeddings helps a lot for zero shot. So then we also investigated, okay, we have all these three spatial priors, those three semantic priors. Do you really need them all? So when we only rely on spatial priors, we can do action classification and action localization to a certain degree. When we only rely on the semantic priors, so having 30,000 object classes, so no localization, we can do a good job for action classification, but we cannot do action localization because we have no priors to indicate boxes. When we combine both, we get the best results. So both classification and localization benefit heavily from having the spatial and semantic priors available. So here are some success and failure cases. So on top, we show the most similar local object according to the WordNet, according to the word embedding. So, and on the bottom, we see the top selected global object, so the classification scores, no localization, so to say. So for the action skateboarding, indeed, there is a skateboard object in Coco, so that is nice, and then we can get a really good result where the ground truth nicely overlaps with the prediction. And also the automatically identified top global objects, skateboarding, skateboard, and inline skate seems to make sense. Then for diving, we have a failure case. So the top local object that was present according to the Coco vocabulary in this case was both. Now, clearly that is not the object of interest, but as it happens, it also misdetected the diver for both. So we are lucky, so to say. When we look at the global objects, the embedding had a better, a larger vocabulary to choose from. So makes more sense. So we have selected scuba dive, diving suit, and diving duck. Then last but not least is the golfing action on the right. So here we confused the two actors. So one is actually playing golf and the other is not playing golf. And part of the confusion comes from selecting the wrong local object, because tennis racket is in Coco and it was considered close enough to be considered. Golf club was not present, so that would have maybe resulted in a better detection. The global objects again seem to make more sense, like golf, professional golfer, and golf club. Now, how does this compare to related work where most other papers rely on attribute representations for their zero shot? So that's why I report on multiple settings, because some people used 51 videos to train or 80 videos to train their attribute classifiers. And no matter the setting that others used, our representation based on objects is so the spatial and the semantic priors is always better. Let's have a look on top, because this is the objects to action paper from Mihir Jain and co-authors. That scored an accuracy of 30.3 on UCF 101. When we add the three spatial priors, we increase further to 32, close to 33%. And when we also add the semantic priors, we again add 3% on top to end up with 36.3%. So this is for zero-shot action classification. Now, for zero-shot action detection, there is not an awful lot of related work. So we compare with our prior work. And here we see that for both Jain et al. With the objects to action and with Pascal Mette's ICV approach, using only the spatial priors, we further improve by adding the semantic priors on all datasets considered. So here we show results on UCF 101. So this is for action classification, where we separated the 101 action categories into 3 meta categories, like person-object interaction, person-person interaction, and person-only interaction. And as expected, our approach favors person-object interactions, but also person-person activities. For person-only actions, such as gymnastics and fitness actions, they obtain lower scores, but this highlights also the importance of having relevant objects available to recognize actions in our approach. So when a relevant action is not present in the vocabulary, of course, our approach will fail because it cannot find the appropriate similarity in the embedding space. We also did an experiment on the challenging AVA dataset. So this is the first zero-shot action localization results ever reported on AVA. We score a mean average precision of 3.7%, which is very modest and indicates that there's still a lot to gain in zero-shot action localization. And although we see some results for person and object interactions like answer phone or playing a musical instrument, here again, the single person actions without any object interactions remain very hard. So, for example, results over here like crawl and falling down, results are really poor. And yeah, having this vocabulary of objects does not really help. So there is an opportunity for more research, I would say. Then having this object representation and also their localization inside the video being known, this enables new types of spatiotemporal video search. So all of a sudden you can ask questions, find me those fragments where there is an actor which has a backpack on his back. And then you can not only find the actor, but also the location of the backpack in this video stream. And because we have the box, we can also ask size related questions. So find me video clips where there is a small sports ball present left of an actor to find this person hitting a baseball. So the semantic representations enables new representation, new applications. That brings me to the conclusion. And open world video understanding with limited supervision is a grand challenge, and there's still a lot of work to do. We highlighted the value of sensory, spatiotemporal, and semantic similarity to, on the one hand, reduce the amount of supervision that is necessary, and on the other hand, to expand to sensory conditions or test conditions that are unseen during training. What is nice about these works is that they are naturally embedded in modern learned representations, and there's really a lot going on in the machine learning field that provides all the tools to further improve upon this work. And I really believe we have only just started to explore the opportunities. And with that, I would like to thank you for your attention, and I'm looking forward to the interactive Q&A after this talk. Thank you.